In this lecture, we are going to switch gears a bit and discuss the kind of data we'll be working with next. Previously, we discussed topics related to the model itself, how a neural network is structured, and the different kinds of functions involved. That's the model. But just as important is the data. Where deep learning and neural networks really shine is on unstructured data, such as images, sound, and text. And so, for the next code example, we'll be moving on to classifying images. Of course, this presents a challenge. Previously, you learned my rule, machine learning is nothing but a geometry problem, and all data is the same. We looked at some pretty simple examples with tabular data, such as predicting whether a student would pass or fail an exam based on how many hours they spent studying and how many hours they spent playing video games. Another example was predicting salary based on factors such as years of experience and degree type. The question now is, if your input data X is an image, how does that fit into this picture? As usual, we're going to start by doing the dumbest thing possible. But first, we have to understand how images are represented in a computer in the first place. So if we just look at an image, let's say the famous Lena image, we can see that the image has two properties, height and width. Therefore, your first thought might be, let's store this in a matrix. The next question is, what do we store in this matrix? Well, suppose I have a matrix A, and I'm looking at the position Aij. This refers to the ith row and the jth column of the image. You might think, okay, so Aij should store the color that appears at this exact position of the image at position ij. The next problem we have to consider is, how do we store colors? In fact, there are quite a few ways to store colors in computers, but in this course, we'll only discuss the most common scheme called RGB. This stands for red, green, blue. Now, I want you to think back to kindergarten. Yes, all the way back to kindergarten. I bet you didn't know that what you learned there would come in handy now. If you forgot what you learned in kindergarten, well, I'm not sure if I can help you. You recall that there's this idea of primary colors. Primary colors are a set of colors from which we can form other colors by combining them. A common set of primary colors is red, blue, and yellow, although red, green, and blue also makes a set of primary colors. So what do you get if you mix red and blue? You get purple. What do you get if you mix blue and yellow? You get green. What happens if you mix red and yellow? You get orange. Now, this one you might not know, but if you mix all the primary colors together, you get white. In fact, from the primary colors, it's possible to combine them in different proportions to get any color. So how do we represent colors? Well, in fact, it's not just a number, it's a set of three numbers. This set of three numbers tells us how much red, how much green, and how much blue. By mixing these colors in different proportions, we can get different colors. So what does this tell us about how to represent images? Well, in addition to height and width, we need another dimension, always of size 3, which represents the three components of color. So our image will actually be a three-dimensional tensor, Aijk. This is the component of the image representing the ith row, the jth column, and the kth color. The next important thing we have to discuss about how images are stored in computers has to do with quantization. Physically, we know that color is light, and we measure it with light intensity. It's a physical value in the real world, and therefore it's pretty much continuous. If it's continuous, that means it has an infinite number of possible values. At the same time, we know that computers don't have infinite precision, and even if they did, we might not want to make use of it because that would make our image files take up lots of space. Well, it just so happens that people have already figured out that 8 bits is good enough. 8 bits gives us 2 to the 8 possible values, which is equal to 256 possible values. These are encoded with the numbers 0 up to 255. So in total, considering that we have the red, green, and blue channels, This gives us 2 to the power 8 times 2 to the power 8 times 2 to the power 8 possible colors, which is equal to about 16.8 million. Now, using this, we can actually calculate how much space it would take to store a raw image. Suppose we have an image of size 500 by 500. Then the number of bits it requires would be 500 times 500 times 3 times 8. That's 6 million bits. If we divide that by 8 to get bytes, we get 750,000 bytes. That's equal to about 732 kilobytes, which is almost 1 megabyte. You might realize that this is quite large for a 500 by 500 image, which is why we have image compression algorithms, such as JPEG, that help us store image files in a much more compact format. As a side note, for those of you who are web developers, this is where hex colors come from. These also happen to use the same color scheme and quantization. So we have 3 bytes, with each byte representing the value for the red, green, and blue color channels. Importantly, 1 byte can be represented with 2 hex digits. Hex digits go from 0 up to 9 and then A up to F, so it's a base 16 number system. 2 base 16 numbers give us 256 possible values, so that's why we need 2 base 16 numbers, or 2 hex numbers, to represent 1 byte. Then, a color, which is represented by 3 of these bytes, would require 6 hex digits. So that's why when you're coding in HTML, colors are represented by 6 digits, where the digits can be 0 up to 9 and A up to F. Now, we can simplify this a little bit if we have an image that does not have color. We call these grayscale images because each pixel can only be black, white, or something in between. Typically, we assign black the value of 0 and white the value of 255. Any value in between is a different shade of gray. And because we only need 1 value instead of 3, grayscale images are stored in 2-dimensional arrays rather than 3-dimensional arrays. In matplotlib, if you try to use the imshow function to plot a grayscale image, it will end up assigning its own color scheme. But note that this is not the true color of the image. This is just a heat map, where we assign one color, such as red, to the high values, and then another color, such as blue, to the low values. So that's why you have to pass in cmap equals gray when you want to show a grayscale image. The last thing I want to mention about how images are represented in computers is that sometimes we don't use 8-bit unsigned integers from 0 to 255. If you recall, neural networks don't like values on such a large scale. So for neural networks, it's more convenient to scale image values to be floating points between 0 and 1. 0 represents no intensity and 1 represents full intensity. And yes, the astute among you might notice that if we represent images as values between 0 and 1, these are not standardized values because they are not centered around 0. There are always exceptions in deep learning. For images, this representation is particularly convenient because it's possible to interpret these values as probabilities. As mentioned, there are always exceptions in deep learning, so here is another one. One of the most famous neural networks today is called VGG, which is used for many computer vision applications such as image classification, transfer learning, style transfer, and object detection. VGG also previously won the ImageNet contest in multiple categories, which, as you recall, is a competition held every year for research groups to present state-of-the-art image recognition models. The interesting thing about VGG is that the original authors did not scale the input data, but they did shift it by its mean across each color channel. Thus, for VGG, images are centered around 0, but the range of values is still 256. So far, we've discussed how images are represented in a computer. However, this still begs the question, how is an image represented as input into a neural network? If you recall, our input data is usually represented by a matrix X of size n by d, where n is the number of samples and d is the number of features. But this doesn't make sense in our case. If we have an image sample, how can it have d features? An image itself is a three-dimensional object. Therefore, it would seem that, in order to represent a data set of images, we would need to have a four-dimensional tensor of shape n by h by w by c, where n is the number of samples, h is the image height, w is the image width, and c is the number of color channels, which is always 3. Now, this is a little bit of foreshadowing, since this is what we'll deal with later, but for now, we are going to do something simpler. To keep things simple, let's say we have a black and white image of size 3 by 3, a very tiny image. Well, we can just number each pixel in a zigzag fashion, going from left to right and top to bottom. So we have pixel 1, pixel 2, pixel 3, all the way up to pixel 9 in the bottom right corner. Well, if we want to represent this as a vector, why not just line them up in a row and call it a vector? So we have a vector of size 9 containing pixel 1, pixel 2, pixel 3, all the way up to pixel 9. We call this process flattening. In this way, we can still store all of our images in an n by d array. Here, n is the number of samples, and d is height times width times color. Each row of this matrix is still one sample, and each sample just happens to be a flattened image. The features of the image just happen to be the individual pixel values. And so here, we encounter again this idea that all data is the same. We saw previously how we can represent all sorts of different tabular data as an n by d array, from breast cancer detection to Moore's law and so on. Now we can represent images in this format as well. So it is a truly powerful concept.